Okay, so Illumination had an idea. One thing we could do here, we could say that segment QS is congruent to itself by the reflexive property, right? Okay, that's a good idea. How is that going to help us prove that those angles are congruent? Elton's got an idea.
If the two triangles are congruent, then all the angles must be congruent.
Okay, there you go. So what we're doing here is we're using the fact that triangles, we're going to use congruent triangles to prove something else, right? So even though the question doesn't specifically ask us to prove that the triangles are congruent, it's useful for us to do so, right? So we could say, if we want to line out some steps here, so we've got, what do we call these things? Steps and reasons, is that what we call them?
Statements.
Statements and reasons. Okay, so we know that, I guess we know here what's given to us is that PQ, segment PQ is congruent to segment RQ, right? And then what else? PS, segment PS is congruent to segment RS. Agreed? Okay, we made the statement that segment QS is congruent to itself because it's being used in two triangles, right? And this was all just given. This was, reflexive property of congruence. And now what? Now that we've added this congruence, what does that allow us to do? Yes, sir. Okay, the triangles are congruent. Now be specific here. How am I going to write this congruent statement for the triangles? Oops, I guess I can't do that. There we go. So, triangle QPS is congruent to triangle QPS is congruent to Q, it has to be QRS, doesn't it? Because we have to get the corresponding angles to match up. And what's my reason for that? SSS. Okay, and now we're there. Now all we have to do here, this is a cool step. All we have to do now is say that triangle PQS is congruent to triangle RQS. I mean angle, did I say triangle? Angle PQS is congruent to angle RQS by, what's my reason?
CPCTC.
That's it. CPCTC. Corresponding parts of congruent triangles are congruent. I know that's kind of a mouthful, but we're going to use that one a ton. CPCTC. Corresponding parts of congruent triangles are congruent. That's it. Okay. So, questions? Okay, so how about this one? Oh, want me to go back?
It's just, why does that thing have such a long name? Couldn't they give it something else?
This one down here?
Yeah.
It's just the way they always do it. It's just the way geometry, the way we do it. It's just an abbreviation. It's kind of like SSS or something.
Is it a numeral?
It is. CP, corresponding parts of congruent triangles are congruent. It's on.
It's on there, it just said that.
Yeah, it doesn't, our somewhat crappy book doesn't have that in there, but I added it to the list of the Moodle list. Okay, and being as we're more proof heavy than the book, I mean, I want you guys to be able to, this is an important step in, for you guys, this is an important thing to be able to do, to use this kind of a step, right? To prove that you're going to use congruent triangles to prove something that's part of the triangles are congruent. That's a good, in the future you'll build upon that concept. Okay? Let's do one more of these. How about this one? Just try this on your own real quick. See if you can crank something out here. mark up on my drawing here to include given information. Arrow, okay, so arrows where? Okay, so an arrow there, and an arrow there. What else?
2 arrows.
Okay, good, 2 arrows, because these are parallel. There's parallelism between those 2 lines, and there's a different parallel relationship between those 2 segments, I should say, right? Okay, good. Is that useful? It's all I'm given, really, not much. Let's talk through our strategy here. What we're really trying to do is show that the left and right segments are congruent. What's our overarching strategy here, do you think? Okay, so, right, we're gonna have parallel lines cut by a transversal. Right away, we can see we've got parallel lines and we have a transversal, so that's probably gonna be a really useful relationship. Good. Okay, we'll go with that. So what's that tell us? If we get, let's take the left and right parallel lines cut by this transversal. What does that tell us? BDA, okay, good. And which one? CBD, good. Everybody see that? That those, and if you want to, sometimes, like I've said before, sometimes it's helpful to just extend the parallel lines in the transversal to see that relationship. Whoops. Are those the, I guess we got that backwards a little bit, didn't we? Which lines would we use for those 2? Top and bottom, right? Does that make sense? So let me go back a little bit. Those are congruent angles, but those are congruent angles based on this relationship, right? Those parallel lines cut by that transversal. Then those are alternate interiors. Agreed? Okay. Now, if we use the other parallel lines and transversal, what angles, what angles are we saying are congruent there? Okay, so BDC, right, and ABD, right? Everybody agree? Okay, so let me erase that. That's pretty messy. So these guys, right? Say it again. And that's what we're going to use, isn't it? Is it
Angle side.
angle, right? So let's add this part. Let's add that step then. So step 2, we can consolidate, and we said that angle CBD is congruent to angle ADB and angle ABD is congruent to angle CDB. And what was my reason for that? Yeah, alternate interior angle. Okay. Now, something that you can actually do with this, like when you go to college and you're doing proof, a lot of times, for the reason that you'll give, if it's any one of those relationships from chapter 3, wasn't it? It was chapter 3 when we did parallel lines cut by transversals, right? Remember we had the originals and then we had the converses? If it's any one of those originals, whether it's the alternate interior angle theorem, whether it's the corresponding angle postulate, etc., in college what you'll probably do is write all of those as just ALT. And that stands for any one of those. We just assume they all basically do the same thing. And then if you're doing the converses, you would write those as conalt. No, it's different. It's different, but that's typically, when you get to college and the proofs get a little harder, sometimes we kind of just are able to say, well, I mean, we can make some shortcuts. We can agree on some shortcuts. We're not gonna do it here, though. So this one would have been alternate interior angle theorem. Good. And then what was the next one? Okay, but in order to do that, we've got to probably say that, right? We'd have to say side BD is congruent to itself by what? Reflexive property, good. What's that?
Well, does it have to be ASA? Couldn't it be AAS? Because you don't have to prove that one side because we're going to keep angles and a side.
You know, that's true. That's, what's that? Why did I write what?
It's B.
BD.
Oh, BD,
You
whoops.
don't have to do that, do you?
Yeah, I don't know why I did that. I do, that step I need, this step right here I need. Because it wasn't given to me, so I can draw in that mark, but I gotta justify it. Okay, and then Emma makes a good point here. Honestly, I don't know if you've noticed this, but do you ever really need, like we gave you this fancy angle side postulate. Have you seen that you really never need it? Let me show you something. You never actually need this. It's kind of convenient because it skips a step, but you never actually need it. If I've got two triangles, and let's say that I know that that angle is congruent and that to that angle, and that angle's congruent to that angle, and that side's congruent to that side. How are those two triangles congruent? Angle, side, but what does the third angle theorem tell us? Right. So, everybody see, we get that one for free. And so anytime that angle, side is the answer, by using the third angle theorem, I also can use what? Angle, side, angle. Yeah. So angle, side is kind of a contrived one. It's not ever really necessary. But we add it. The only reason we add it is because it saves us a step. Then we don't have to use the third angle theorem. Yeah. Okay. So then we would say that triangle. Oops. So step 4. Make a congruence relationship here for the triangles. What are we going to get? Triangle ABD we'll start with. Is congruent to triangle what?
CDB.
ABD would be CDB, right. By ASA, and then finally we got it right. So now we can say that side AB is congruent to side CD by what? That's it. Okay, got a question for you. This step is very precise, isn't it? Do I have to write, when I come down to this next step and I want to say that side AB is congruent to side CD, could I have written that as side AB is congruent to side DC?
Yeah.
I could, because even though we're getting there because the triangles are congruent, these two sides can be named, there doesn't have to be a direct correspondence there, right? They're just, what makes segments congruent? Their measures are equal, that's it, right? So, do you see the point I'm making? It's probably not a bad idea to line these up the way they are in the triangle, but I could have switched those endpoints around, and the segment congruence is still the same, right? Because sides and segments are the same thing. You see what I'm saying? We never had to deal with, we've been dealing with segment congruence now for a long time, and I've never been very particular about getting the endpoints in a specific order, right? So we still don't have to. Okay? Make sense? Okay. When are we out of here? 36. So it's probably not. So what are we given here? A is the midpoint of MT. A is the midpoint of SR. We're supposed to prove that segment MS, and you can't see that, but that's supposed to be an M. I don't know why that's not looking like an M. That's supposed to be an M. I'll fix it. I'll fix it right now. Okay, we're supposed to show that segment MS is parallel to segment TR. Illumination, get an idea?
Segment SA and segment AR.
Okay, good. Now, how are we going to, that might take a couple steps. How are we going to probably have to, well, technically we'd probably have to say the length of AS equals the length of AR by the definition of midpoint. But honestly, you know, what does that really bite? Why can't we probably just as easily might say, and this is the way I would have proved this in college too, I would have just said this. You know those are congruent by definition of midpoint minus one little step, right? Does that make sense? And I'm fine with you doing that. And then, it's hard to do without writing on the board. Then those two are congruent, right? Okay. So, now what? What do you think?
Vertical angles.
Okay, we got vertical angles. And that's enough for us to say what then? Okay, so now we got congruent triangles by side angle side. Okay, but we still have to get from congruent triangles to showing that those lines are parallel. Now, so we move into kind of a new phase of this proof. How are we probably going to have to show that those sides are parallel? How do we generally prove parallelism? What's really the only way we've done that? Now, later on, we'll have some other ways. But now, there's been only one way we've been able to do it. It's been a chapter 3 thing, right? Was that? Say it again, Emma. Well, I mean, we could.
Transversal.
Okay. Go ahead. Yeah, go ahead.
Since they're equal distances apart because of the body congruent.
Not exactly. We did. It had something to do with transversals, didn't it? Right. Remember, we had two groups of relationships in chapter 3.
CPCT, C will give us the MSA,
Good.
and RTA are congruent, and then from that we can use the alternate interior angle
Converse. Okay, good. Remember, in chapter 3, we had two groups of relationships with our transversals. We had the original said, if parallel lines are cut by a transversal, then a bunch of stuff is true. Alternate interior angles are congruent, corresponding angles are congruent, etc., right? The second group were the converses, and those are the ones that said, if these angle relationships exist, if corresponding angles are congruent, or if alternate interior angles are congruent, then the lines are parallel, right? So it's the transversal converses are the ones that allow us to prove lines are parallel, right? So Elton had an idea. What he said was, we've got these triangles congruent to each other now by SAS, right? So then let's go ahead and say, okay, now by CPCTC, there are some congruent angles, right? Because isn't S corresponds to R, doesn't it? Does everybody see that? It occupies the same position in the left triangle that R does in this triangle. Everybody see that? It's between. How do we know that? Well, S is the angle formed by the one hashed segment and the no hashed segment, right? One hash, no hash, right? Okay, so then by CPCTC, those are congruent, so that tells us then if alternate interior angles are congruent, then the parallel line, then the lines cut by the transversal are parallel, right? So we got it. It's cool proof. That makes sense? Okay. Alright. See if we got about a 5-minute one here.
So do you want me to turn in 4.2, give me that one?
Oh yeah, let's look at 4.2. Oh, that's a good one. We'll do that one some other time. Okay, let's look at 4.2. Can I just pull yours up, Kirk?
Yeah.
Okay. Okay, that's the one right there.
Expression.
Oh, whoops. That's the one right there?
Yeah.
Okay. So, yeah, so when you put in, if you put in triangle like XYW is congruent to triangle ZYW, it didn't take it?
Oh, without, we were all trying to.
Oh, no,
say
whoops.
yes.
So that would be which one? Yeah, it would be SAS, right? Yeah.
And I tried it like capital.
Oh, no, you shouldn't have to, yeah. So that one's messed up. Yeah, just turn it in. Turn it in, I'll fix it. Yeah. Okay.
Wait, I just put triangle ZYW is congruent to triangle XYW.
Oh, and that was right, wasn't it? Yeah. Yeah, that's what they're asking. Actually, look. See, that's what they're asking. Yeah, I didn't read the question.
Oh, I see.
They don't want you to say SAS, or they're asking if two triangles can be proved congruent, write a congruent statement. Right? And if not, write NA. Yeah.